Swayam Prabha. Digital India. Educated India.
Now, depending on the function values, suppose if we have the function value which is x2 is better or minimum than the x1 as well as the x3, then we know that our minimum value lies between x1 and x3, and we can end the process right there. If we find out the new points which we obtained from the initial point x1 are worse than the initial point, in this case we are using the minimization function, so the objective function value at those 2 points are higher than the objective function value at the first point, which it indicates that the minimum is going to lie between x1 and x2, and we can end the process because we are only going from the lower boundary towards the higher boundary, and in this case x1 represents the lower boundary, so there is no way of going any lower value than this. The third option, when we find the new point whichever we are getting are better and better than the initial point, in that case we can actually move forward and we can say my new x1 point is the x2 point, the new x2 point is the x3 point, and the new x3 point is obtained from the new x2 point by adding the fixed step size to with it. Once we do that, we go to the next step where we check whether we have reached the other boundary or not. So if we had reached the higher boundary, means we cannot go any further, we can stop there. If it is less, means if we haven't reached there, then we can go to the step 2, which is here, where we want to compare the function values and decide the process and make decision on the process. This process will go repetitively till we reach the other boundary, or we reach to a point where we find that my first point is better than the next 2 points, which is x2 and x3, or my second point is better than the first and the third point, which is this condition. In all these cases we are going to terminate, and then we are going to report the boundary of the objective function value. Now in this case, as I was indicating, the accuracy is twice the step size, because we are reporting the two values which are of twice the step size apart, except in one case. In this case it is only one step size apart. So the accuracy is generally can be indicated by 2 times b minus a divided by n, and if we know the accuracy we can choose that and find out the number of steps needed to reach their accuracy on an average. And in this case, once we know the number of steps needed, we can easily calculate the number of function evaluation required. So that is given by n by 2 plus 2. This is on an average, not always. If we reach the optimum solution somewhere where this condition is satisfied, the first condition, then we may have less number of function evaluation, or we may have, but if we are reaching towards the end, means when the minimum value lies between this, then we are going to have maximum number of function evaluation. So depending on the number of function value evaluation required, on an average is going to be of this amount. So let us first see how this method work in a graphical representation. If my objective function looks like this, which is an unimodal, in this case we have only one optimum solution which lies here, and our boundary suppose is here, this is my A, and the other boundary is here, the higher boundary is here, which is B. Now initially we are starting saying that this is x1, we are taking the step equal to S, and this becomes my x2. We are looking into the function value here, and this is my third point, again same amount of step size, which is x3. And in this case we see when we compare the function values, it is reducing in all the three cases. Then we are saying this point becomes x1, this becomes my x2, and a point here of s distance is going to become my new x3. And again we compare the function value here, here, and if we see it is reducing, we are going to replace the x2 as the new x1, x3 as new x2, and this could be my new x3. So now if we compare, we'll see that the objective value here is higher, here it is lower, and here it is comparatively higher than the middle point. So we can stop at this process and report these 2 points as the bracket of the optimum solution. So we'll be reporting x1 comma x3 as the bracket. Now if we come to a condition where we find that our start point is somewhere here, this is my A, so let the higher boundary be here. From here if we start S distance, so this is my second point, so the first iteration A is equal to x1, this is my second point x2, and this is my third point which is x3. In this case, if we see the objective function value, we can clearly see that the objective function value is minimum here, and as we move towards our right, the objective function value is increasing. For a minimization problem, we are going away from the minimum possible solution, so we need to stop right there and report this as the bracketing points for the minimum solution. Now in this case we are saying that this is the bracketing point because we did not investigate in between points. In this function which I have shown in the blue line is quite clear that it is increasing in between these 2 points, but you could have a function which could look like this, and in that case our optimum solution could be somewhere here. So for this reason we are saying it is between these 2 points. Now the third situation could have been like, if we keep on moving in, let's look into the another boundary condition. My higher boundary is here and my lower boundary is here, which is B. So as I move, we'll find that we'll come to a point when the next point is going to be here, and this is outside the boundary point. So we cannot use this point as the bracket point, rather we have to say the bracket is going to be from here to the previous point here. So in that case we are saying the bracket is between x1 and B. So these are the three different conditions. In first case it is between x1 and x3. In the second case it was between x1 and x2, and in the third case it is between x1 and B. Now we'll look into an example which will help you to understand this method even better. In this case we are required to minimize this particular function, which is x square minus 54 by x, and we have the restricted range of the function between 0 and 5. So once we know this thing, we need to see what is the accuracy we want. We want the accuracy of 1, which means the bracket which we are going to develop should be within 1, should not be more than 1. So let's look into the solution. First we need to find out the maximum number of iterations we may need to reach the accuracy we intend. In this case the accuracy intended is 1, and if we equate it to this twice the step size, if you recall, then we can get the accuracy. From this case we can find out the n value is going to be 10. If we use this 10 to find out the step size, then we get the step size as 0.5, and if you want to find out the average number of function evaluations we may need to do, we can use this formula where we fit in the values, then we know that we may need to do 7 function evaluations. So now let us start the process. We are starting at the first point, a is equal to 0, so that value is assigned to the first point, x1 is equal to 0. At that particular point my function value is going to be infinity, and if you are looking into the second point is obtained by adding the step size with the first point, which is going to be 0 plus 0.5, which will be equal to 0.5, and the function value at that point is going to be 108.25. The third point is obtained by adding the step size with the second point. So my second point is 0.5, with that we are adding the step size 0.5, and we are getting the third point as 1, and the function value at that point is 55. Now it is clear that the function value is reducing as we move from x1 to x3, and if we see this, basically we can say my new x1 is the x2, my new x2 is the x3, and my new x3 is going to be the x2 plus s. This process is going to be repeated. Here we'll see in a tabular and graphical format our solution. So we started with our initial solution at 0.0, and then we found the next point, which is 0.5, the third point as 1. We find the function values at the 3 points. We see that the function value is reducing, which means it is satisfying this condition, so we said yes. So accordingly we adjust my new x1 is the x2, which is going to be here. My x2 new x2 is going to be the x3, which is going to be here, and my new x3 is going to be the s plus the x2, so it is going to be 1.5. so the function values are shifted here, so we need to find out the function value for x3, and this value is here. Again, the condition is satisfied, means my function value is reducing as we increase the x3 value, or as we progress towards the x3, and hence this is satisfied. The process keep on moving till we reach a point. At this point you will see that once we find our new x1 is this, new x2 is this, and the new x3 is this point. At this point my function value is going to be 27.68, which is higher than the function value at the x2 point. So it is clear that my function value at x2 is lesser than the function value at x1 as well as the function value at x3. So we cannot go any further. We need to terminate the process. This condition is not satisfied. So we can now report that the bracket is going to be 2.5 and 3.5, which is this value and this value. If you see, the precision here is exactly 1, and therefore the minimum is going to lie between this one. If we want to represent it graphically, we started with 0, which is going to be infinite somewhere up beyond the graph. Second point is here 0.5 and 1, so the function value is reducing. In the second iteration, this becomes my x1, this becomes my x2, and this is my x3. So again we see the lowering trend. So again we are moving. Now we are going to consider this point, and this point. Out of this 3 point, again we are seeing that the function value is reducing. So now we'll move to the this, and this. Again we are seeing it is reducing. So now we'll move to the this point, this and this. We see the similar trend. So then we move to the this point, this and this. Once we move to this, we find this is marginally better than the points which are on either side of it. So we stop the process right there and report this point and this point as the bracketing point, which is 2.5 and 3.5. Hope you understood both the bounding phase method and the exhaustive search method in this lecture. So in today's lecture we learned about the two different elimination methods. One is related to the bounding phase method, the second one is related to the exhaustive search method. If you have understood both methods, you realize the bounding phase method is very similar to the accelerated step size method in the unrestricted search method we had discussed in the last lecture. In fact, it is another way of doing the accelerated steps size method, whereas the exhaustive search method is a method where we do need to know the boundary of the search space. If you see both methods, one glaring difference which is going to come out is that the bounding phase method, the accuracy could be very low if we need higher number of steps to bound the optimum solution. So the difference between the two bracketing or two edge is going to be high. Whereas the exhaustive search method, we can actually control the accuracy of the obtained solution. You will also realize that by any chance, if we choose a point which is far off from the optimum solution point, then exhaustive search method may take longer, particularly if the step size chosen or if we want very high accuracy. So one has to be careful with the accuracy or the step size considered in the exhaustive search method. Whereas in the bounding phase method, no matter what step size we choose, it is going to come closer to the optimum solution. If we choose the initial guess point closer to the optimum solution, then the accuracy is going to be better and we can reach the optimum point sooner. Today's two methods, and in the previous lecture the two methods we had discussed, it helps us to bracket the optimum solution. Once we bracket the optimum solution, we need to move to the next level where we can move closer to the optimum solution, and there are various methods as I had indicated in the last lecture. We'll see some of those methods in the coming lectures. First we'll start with the region elimination methods. There are few methods which are quite good in doing that. We'll discuss about those region elimination method in the next lectures. So till then, thank you. See you in the next class.